Now we have another clustering data model using the expectation maximization algorithm. Clustering data model, as you have seen in the previous clustering task, it is used to group customers into similar collections, into similar clusters. And the members of a cluster are similar to each other in some way. We may not know exactly how they are similar to each other, but the system gives us the information and finds this similarity between the members of the cluster for us. This is not a supervised machine learning task. This is unsupervised. So in the clustering, we don't have pre-created groups of records like we have in the classification, where we have those labels defined by a human operator. In clustering, the machine will identify the clusters and will basically create the classification for us. So we do not give the machine anything, just the data with the attributes, the basic attributes of the data. So I'm going to give them, in this case, the entire table to the data set I'm going to use for clustering using expectation maximization. So I'm going to synchronize the data, and I'm going to give all the columns, including the LTV and LTV bin, the labels and the numbers of the lifetime value we have used in regression and in classification tasks. And I'm going to split this data in the 75-25% ratios between the training and testing data. And I'm going to define my two objects from the two splits I just created. The first one is going to be used for training, and the second split, 25%, is going to be used for testing. I'm going to also specify some settings for my expectation maximization algorithm. You can click on the link and see all the settings in case you are interested to know more about this algorithm. And then I'm going to create the object, the machine learning model itself. This is a Python object called em_mod right now. And I'm going to fit my training data into this object, into my expectation maximization learning model. And this is when the learning model, machine learning model, analyzes the information, my records, and it identifies the data and those clusters, basically, those if there are clusters in this data, if there are similarities between those customers. And now I can print all the details of the model. Here are the details: expectation maximization, clustering, all the hyperparameters, which are, most of them are using the default values, and then computed settings. And one of the, maybe the most important parameters we have always, we always have to check is the converged. The convergence means that the optimal solution has been reached or not. And the iterations of the optimization for the machine learning has reached to an end where you can use it for prediction, basically, to get values on testing data which is not labeled, or it doesn't have values. So in this case, the converged parameter is no. The value for converged is no. So in this case, we can say that the model has not reached convergence, and it hasn't reached that equilibrium where we can use it to train it and to retrieve, then to use it to execute it, to retrieve predictions using that machine learning model. It doesn't have the capacity to provide predictions. So if you want, you can check only that parameter individually in the complete output here. So you can filter the converged parameter from the whole output I have in the previous block. And I'm going to identify and to investigate why it has not reached convergence. First, the expectation maximization algorithm requires a limited set of attributes for the data. And I gave it the whole data set, which has 29 or 30 attributes, which is too much already for this algorithm. So in this case, I'm going to identify maybe the most important attributes for this task and use only those attributes. And maybe I'm also going to increase the number of iterations for my model to converge, to reach the convergence. So now I'm going to change I'm going to rank the attributes in the importance order. And here the attributes ranked by the importance in this for this model in particular. The first attribute has been identified as the house or ownership, and it has a 33% importance in my for this model, in particular for my data set. And then the mortgages, if the customer has mortgages or not, the amount of the mortgage, and then the two labels or the values we used for prediction are also very important, the LTV and the LTV-BIN, and the how long this customer has been with the company, time as customer, and then number of dependents in the family, the marital status, which is the 8th here on the attribute importance for this clustering expectation maximization models we are running right now. So these are the most important attributes, and we can see here in the order of importance, in the descending order of the importance here until the end. The customer ID, which is basically the ID of the customer, has absolutely no importance because, of course, this is just a value used to identify individual records. And I'm going to increase the number of iterations to 200. I think it was 100 before in the previous execution. And I'm going to recreate the expectation maximization machine learning model with my new settings. And then I'm going to use the most important attributes in my training task, in my training execution from my data set to train this model and to see how it performs. So I specified the 1, 2, 3, 4, 5, 6, 7, 8, I think 8 attributes from the 29 attributes. I have limited my model to only 8 attributes, the most important ones, in order to improve and maybe reach the convergence for this machine learning model. So now I'm retraining the model with only the columns from my data set, which I have identified as being the most important attributes. And now I'm going to I'm going to display the parameters and the details of the clustering expectation maximization model, machine learning model. And again, I'm going to check for the converged. And here we have it. It's yes. So this time we can use it to actually run this machine learning model to get predictions for the clustering of our customers, for clustering and the segmentation of the customers we have in this data set. You can call it customer clustering or customer segmentation. It can be used for both. So now I'm going to use the model to make predictions on the test data. On the second set of the split, I have saved for testing, not the one I used for training the model, but one I'm using for testing. And I'm going to add as supplemental columns the customer ID, last name, first name, and the LTV bin value, just to and try to identify if there is any relationship between the clustering or the segmentation produced by this unsupervised machine learning model and the classification, which is pre-labeled by our human operator into those LTV bin labels or classes, low, medium, high, and very high. So let me show you the results here. So we have the customer identification columns. We have the LTV lifetime value bin class, and we have the cluster ID. We have identified 4 clusters, and we are trying to check if they match with the classes we have already in our pre-labeled column with the name of LTV bin. So let me sort it by the cluster ID, and to show you only the cluster IDs, individual cluster IDs. We have 4 clusters, 3, 5, 6, and 7. These are the clusters we have. The expectation maximization model has identified in our data, and we can count the member of the clusters grouped by the lifetime value. So in cluster number 3, we have 64 customers which are high class customers, 309 which are low class customers, and 569 medium class customers. In cluster number 5, we have some high class customers, 1 single low class customer, some medium class customers, and 1 single very high customer. So this is how it looks like. This is it's easier if we visualize data into a chart to see exactly how they map between the predefined classes and the 4 clusters we have identified. Let me see if my scroll. Okay, so we can investigate if there is any relationship between these clusters, the segmentation which has been provided by the expectation maximization and the 4 classes. And we can see here that between the LTV, we have ordered this in descending. So we have printed now the LTV actual value, the lifetime value, numerical value, along with the class and the cluster ID. And we're going to use this value to plot the customers into a graph showing this value and the cluster ID, just to show how the customers are distributed in each cluster based on the LTV numerical value. So this is the plot here. I'm going to replace the cluster ID with a numerical order. So cluster number 3 is going to be the first one. Cluster number 5 is going to be the second one. Cluster number ID 6 is the third one. And cluster ID 7 is the fourth one, the last one. Let me do the plot just to show you. So here are customers distributed by the LTV value and in which clusters, they have been segmented, identified. This is the cluster ID 3, cluster ID 5, cluster ID 6, and cluster ID 7. We can see based on the LTV value, they are overlapping. So we cannot say that the clusterization can be identified or has the same rules behind or the same logic as the LTV classification we have used in the previous tasks. So this clustering may be based on different arguments, on different attributes, not the LTV lifetime value of the customer, which is like what I was trying to show here. So we have many values which have the same LTV numerical value, but they are in totally different clusters, which doesn't have any relationship between the cluster and the class or the lifetime value of the customer. So this is how it works like. Thank you very much.